Poisson distribution as an approximation to binomial distribution. Okay, as we already discussed, Poisson distribution, we are going to have some specific period or specific area or specific time there. And if you're going to have we're going to use as an approximation to binomial when the n is large and the p is small. Okay, so maybe you can have some rule here when the n is more than or equal to 20 and the probability is less than or equal to 0.05, or maybe n is more than 100 and the p is less than 0.1. So you may use this kind of help. So which is better result will be having p approaching to 0 and n is the higher of n, which is approaching to infinity, and the p is approaching to 0, which is the least p. So maybe you can use this one as an example. Just proceed with example 8.15. Given that each computer contains 1,000 electrical components, probability that one of those components fail to work normally in one, you consider 0.0022. Consider that each function of the components will not be interrupted or interfered by the other components' functions. Estimate the probability in 1 year. Okay, in 1 year. Okay, it is said here, 3 components fail to work normally, between 1 and 3 components inclusive fail to work normally. Okay, you may read by your own again this question, but just proceed. If you try to look in the question, try to extract the information, try to put out in the information, you can put over here x is equal to the number of components fail to work normally, and x is binomially distributed because we can say that which is number of components fail or not fail. So you can see over here the probability of having here 0.0022, which is less than 1.10, and the n is equal to 1,000, more than or equal to 50, which is you can refer from the first criteria here. So then the next one, we're going to have your Poisson. Okay, easy to say. Example 8.5. If you read the question, it is given in the binomial distribution. It is given in the form of binomial distribution, but the n is large and the p is small. So that's why you are going to have some help from Poisson distribution. So if you try to look at here, the p is 0.0022, the n here is 1,000, is it right? So as we know, for the mean for the binomial distribution, we'll be having 0.0022 multiplied with 1,000, we'll be having 2.2. Why we need to find the mean? Because of what? For the Poisson, we are just having our lambda. Lambda is defined as the mean for the Poisson. So that's why we'll be having this one. Now, as I'm going to repeat again, this question given to you in the form of binomial distribution. So, but what? The n is too large and the p is too small. Not too small, it is a small. Then the next one, we're going to find your mean. Why we need to find the mean? Why? Because of what? We are going to use your mean inside of your Poisson distribution, because we are going to have some help from the Poisson here. So the first question asking 3 components fail to work normally, so probability of x is equal to 3 between 1 and 3 component inclusive, which means between of 1 and 3, which is 1 and 3 is included, x is equal to 1, x is equal to 2, and x is equal to 3. So therefore you can get the answer there. So let's proceed, which is example 8.16. Already have a solution, don't worry. On average, 1 in 200 cars break down on a certain stretch of roads per day. Find the probability that on a certain day, none of sample of 250 cars break down, more than 2 of a sample of 300 cars break down. So if you try to read properly, so we will be having a binomial distribution again, which is number of sample of 250 cars break down as x, and n, which is equal to 250. How can we know a p? P will be equal to 1 over with 200, which is it is said here. On average, 1 in 200. 1 in 200 cars break down. It doesn't have probability, right? But it is given in hidden one here. Probability is equal to 1 over 200. So we'll be having what? 1 over 300 will be a small number, right? N is a large number, right? So that's why we'll be having a Poisson distribution as approximation to binomial distribution here. So the lambda will be equal to N multiplied with P will be 1.25. So X is equal to 0. So you'll be having this one. For question A, more than 2, we'll be having just a little bit different. As for question B, more than 2, yes, of course, but it is given a new sample, a sample of 300 cross breakdown. So sample of 300 cross breakdown, so you need to start from the new one again, which is N is equal to 300, the P will be equal to 1 over 200. Okay, careful because the probability is still having the same probability. So the lambda will be having 1.5. So we just want X more than 2 here. So 1 minus probability of X less than equal to 2. So we'll be having this answer. I hope you are clear. Okay, I'm just going to repeat again, which is for this part, Poisson distribution as an approximation to binomial distribution. In easy way to say, you can see from example 8.15 and 8.16, which they are given in the binomial distribution situation, but the N is large and the P is small. You may put some notes there. Or the N is small, this is some guideline, the first guideline, or maybe you can have the next guideline, which is this one, and more 100 and P less than 0.10. Okay, so for the next one, which is next example, which is, of course, it is not actually 8.22, but just given that, so we're going to label it as an example 8.22 here. I already have answer, but it doesn't have a solution. I'm just going to give some hints there, which is the probability here. Probability for this example will be equal to 0.004. which is comes from where? Comes from the 1 out of 250, which is comes from here 0.4%. Okay, and the N is equal to 80, which is contain 80 articles each. So in this case, you need to find what? You need to find the lambda. The lambda will be equal to 0.32. And the first question asking of the boxes are free of defective, which is X is equal to 0. So you already got this answer here. And the next one, X more than or equal to 2, which is contain 2 or more. So you will be having this answer. And the next one, if 2 boxes are taken randomly, what is already the total number of defective articles is 1. So here, this is the new information. I'm going to give information here, which is you'll be having N is equal to 160 because we'll be having 2 boxes, is it right? And the probability is still 0.4%, which is having the same pre here. And the lambda, the new lambda will be equal to 0.64. And we just want probability of X is equal to 1. So this is your answer. Just try it first. And the last question, example 8.17 here, which is already have answers. If you want to have some hints for question A, you'll be using for question A, you'll be using binomial distribution. Okay, what is your N, what is your P, and use your binomial distribution formula. As for question B, since we are having process of 96, so it will be a large, and the P is 0.03. And as for B1, you need to find using the Poisson distribution as an approximation to binomial distribution. You may refer from the previous example. And the next one, which is question 2, it will be a little bit tricky, but just try it first. Actually, you'll be using binomial distribution by having answers from B1. Try it first. If you cannot do it, just do let me know, remind me. Sometimes I forget about this one, okay? So that's all for the 8.2.